autonomic nervous system. And we talked about the two different divisions here. So we're going to look at them separately. We have the sympathetic. We have the parasympathetic. And then we're also going to talk about the somatic and how that compares. And sorry I'm writing this cross, so I just want to have enough space to draw these tracks out. So we start with the cross-section of our spinal cord. And these are going to arise from different spots on that cross-section. Okay, so for the autonomic nervous system, we know that this is arising from the lateral horn. Okay, so we draw out our little horns here. And then from the lateral horn, both the parasympathetic and the sympathetic fibers are going to arise. Okay, however, they're going to be different segments. For the sympathetic system, it's going to be cranial nerve 3, 7, 9, and 10. For the sympathetic system, we said it's going to be T1 to L2, the thoracolumbar segments. T1 to L2. Okay, so let's think about how the parasympathetic starts. This is going to have a long preganglionic neuron that arises here. It's going to exit through the ventral root. So don't get confused about where it's starting versus where it's exiting the spinal cord. Starting at the lateral horn, exiting through the ventral root. And then it's going to be composed to form the preganglionic neuron, which we said is going to be long. It's going to go all the way out to a ganglia that is very close to the effector organs here. And then a shorter postganglionic neuron. Let's make this a little long. Oh, no. Okay. So a long preganglionic, and then a short postganglionic neuron, and then out to its effector tissue. And then we're going to talk about the neuroeffector junction in just a bit, but this can be various structures that are being affected. So cardiac muscle, smooth muscle, adipose, or glands. Okay, this will go for both the sympathetic and parasympathetic. For the sympathetic division, we have a short preganglionic neuron, and then a much longer postganglionic neuron, going all the way out to the effector organ as well. Okay, now let's describe some of the anatomy here. First off, we want to think about these locations as ganglia. These are called autonomic ganglia. Right, in both scenarios. For the parasympathetic system, it's a bit more straightforward. There's only one type of autonomic ganglia. For the sympathetic system, we have three options, right? We have three routes for this preganglionic neuron to synapse. The first is to the sympathetic chain. So this ganglia could be a part of the sympathetic chain. This ganglia could also be a collateral ganglia, so not a part of the sympathetic chain. Or the third option is involving the adrenal medulla. So this preganglionic neuron could synapse onto the chromaffin cells of the adrenal medulla and result in hormone release from those cells. So the adrenal medulla is a third route of synapsing here. Now, again, autonomic nervous system only has one route. There's no ganglia, there's no parasympathetic ganglia, there is no synonymous structure in the parasympathetic side. For sympathetic, we have three different options. Let's label these out. So this is the preganglionic, and this is a postganglionic. Okay, and same thing here. All right. Now let's talk about the anatomy of the myelination of the fibers here. So we have gray ramus fibers versus white ramus fibers. When we leave the spinal cord, and again, this is happening in both divisions of the autonomic nervous system, when we leave the spinal cord and we enter the preganglionic neuron, so from this spot through the ventral root, emerging to become a part of the preganglionic neuron, this is referred to as being a white ramus fiber because it's myelinated here. So this is a white ramus fiber, and that means that it is myelinated. Okay. It's going to enter the preganglionic neuron, travel to the ganglia, and then at the ganglia, it's going to synapse, but then re-emerge into the postganglionic neuron. And in that instance, it's going to become a gray ramus or a non-myelinated fiber. All right, so let's change the color here. So this is now going to leave the preganglionic neuron and re-emerge into the postganglionic neuron. And in this instance, it will be a gray ramus fiber. And it will be unmyelinated. All right. Let's talk about the types of receptors and types of hormones, or sorry, neurotransmitters that are released. The only hormone will be from the adrenal medulla, but in the other instances, it will be neurotransmitters. So we know that all preganglionic neurons release acetylcholine. So we can put acetylcholine into the nerve terminals of both of these preganglionic neurons. In the parasympathetic side, the postganglionic neuron also releases acetylcholine. So there's also acetylcholine released here. However, the area that they bind to are going to be different. On the postganglionic soma, this is going to be a nicotinic receptor. Nicotinic, which we also said is ionotropic or fast. Right, let's put that here, fast. Versus when it binds to the effector tissue, wherever that is, the acetylcholine here will bind to muscarinic receptors. All right, and these are, while they're both cholinergic, one is fast and one is slow. In terms of the sympathetic system, similar at the ganglia, we have acetylcholine binding to a nicotinic, let's put this here, nicotinic or fast receptor. And then when it gets to the neuroeffector junction, the sympathetic side, this is where we have adrenergic neurons. So these are not releasing acetylcholine, but they're releasing norepinephrine, some degree of epinephrine, and then even a tiny bit of dopamine. Okay, but norepinephrine being the main one here. And then that will bind to adrenergic receptors. And we talked all about the adrenergic receptors. We can have alpha 1, alpha 2, we can have beta 1, beta 2, or beta 3. So definitely we'll review this a bit as well, the difference between the receptors, how they behave, their second messenger, etc. But we also want to make that connection here, that the sympathetic system has different receptors, different neurotransmitters engaged. Let's talk about the uh, overall effects. So just looking at the overall functions of both of these divisions as well while we're here. So we can think about the parasympathetic as being the rest and digest. Okay, very important. We want to slow things down here. Heart rate slows down, respiratory rate slows down. We have bronchodilation instead of constriction, or sorry, we have bronchoconstriction instead of dilation. We have increased glandular secretions. That would be all of your salivary glands, gastrointestinal motility. All of that would increase with the parasympathetic division. For the sympathetic division, this is the fight or flight, right? Fight or flight. Also freeze sometimes, the fawn effect can be elicited here. So fight, flight, freeze, oops, would be the overall function of the sympathetic system. Okay, make sure I'm not missing anything here. So we refer to this as being the ganglia. We said that this is the nerve effector junction. And we talked about some of the differences of the nerve effector junction. For one, the greater distance. For two, the presence of varicosities. Okay, so those are two main differences between this nerve effector junction and this traditional neuron to neuron synapse. So that's important as well. Let's focus on the somatic system and think about how that compares. So the somatic nervous system, now we're going to have fibers arising from the ventral horn. So ventral horn is where they arise, and then they also exit through the ventral root. And here we're going to have one neuron, one long continuous motor neuron that goes all the way out to the muscle. Okay. Have our neuron ending here, so not a varicosity, and then we have our skeletal muscle. So another important distinction is that the somatic system is voluntary. Let's kind of star that here. The somatic system is voluntary in terms of the way that we control. This is voluntarily controlled. The parasympathetic and sympathetic systems, both divisions of the autonomic, are involuntary. All right, so these are involuntary. In that we can't control these cognitively, right? But we can control skeletal muscle. So skeletal muscle is the only tissue that we are innervating here. Now, the neurotransmitter and receptors are pretty straightforward, always acetylcholine and always nicotinic fast receptors. So one receptor and one neurotransmitter. And then the name of this neuron is also different. This is a motor neuron. Okay, so that's just some of the major differences. We also want to refer to this junction as a neuromuscular junction. So not a nerve effector, but a neuromuscular junction here. Right? Versus what we see in the sympathetic side. Okay. Any questions from this? I feel like this covers the entire neuro muscular system and the autonomic system in terms of most of the important aspects worth remembering. Okay. Great question. So for the adrenergic receptors on the sympathetic side, there is no nicotinic when we get to the postganglionic neuron. So the preganglionic neuron does have nicotinic, right, in both instances. In the parasympathetic side, the postganglionic neuron has muscarinic, right? So those are going to be both types of cholinergic. But in the sympathetic side, the postganglionic neuron releases norepinephrine or epinephrine, so it's an adrenergic neuron, and it's going to bind to adrenergic receptors. So there is no muscarinic receptors on the sympathetic side. All right, there's a very small exception that we talked about, which was sweat glands. But for the most part, the sympathetic postganglionic neurons will release norepinephrine. And depending on the tissue, so the specific tissue here, this can be smooth muscle found in blood vessels, where it would most likely be an alpha receptor. This can be the heart, where it will be a beta-1 receptor. This can be the lungs, where it will be beta-2, adipose, where it will be beta-3. So depending on the exact tissue, we will have a different type of adrenergic receptor, and then even more complex will have a different type of receptor response, right? But it will all be slow responses or what we call metabotropic. So it's going to involve a G protein and a different type of response, which is tissue dependent. Great. Let's see, another question here. Do the fibers leave the ventral horn in the sympathetic system too? Yes, correct. So both exit through the ventral horn, the ventral root, excuse me, not horn. Right, let me just make a clarification here. So the fibers are arising at the ventral horn in the somatic system, arising at the lateral horn in the autonomic divisions, but both instances, both the somatic and the autonomic, they're all going to exit through the ventral root, which is leaving the spinal cord through this emerging root here. All right, so they all exit through that ventral root, but they are arising from different places on the spinal cord.